Hello, everybody. Thanks for staying to the end of the day. And it's great to succeed such a good sequence of talks. And I'd like to just give a nod to some of the talks that demonstrated good data collection management and curation, ongoing curation, as those are underpinnings that are absolutely essential for the project that I'm going to talk about. So I'm addressing Canada One Water. We're interested in modeling the water cycle of Canada, and the driver is water management sustainability under climate change. So it's an adaptation question. And I'd like to acknowledge my co-author and co-project lead, Stephen Fry, who's at Equante. And of course, we're not doing this as two individuals. So we have a great team supporting this initiative, both at Equante, within the Government of Canada, at a variety of departments and sectors and branches, and in academia at the University of Waterloo and the University of Toronto. This project is funded across a number of agencies or departments. And just to give a highlight from the top two rows of this this diagram, initial funding for this project was from Defence Research Development Canada through the Canadian Safety and Security Program. And then funding was expanded through the Geological Survey of Canada and Agriculture, Agri-Foods Canada, with Dave Laipin and particularly his Environment Change One Health Observatory project. There are a lot of issues and reasons why we want to have an improved understanding of groundwater surface water, and this slide sort of in some images rather dramatically demonstrates the range of issues associated with both climate and with groundwater surface water availability. And on a more sort of friendly note, 30% of Canadians rely on groundwater for potable water. And in rural Canada, that can range up to 60%. And I think, as many of you would be aware, Prince Edward Island actually is 100% reliant on groundwater. And the black dots in this map, which is from ARERA 2014, just highlights the distribution of municipalities that rely on groundwater in Canada. And it's always good to have rationales that are presented by other individuals or groups. And so on the right then is why do we need Canada One Water? And it's a rationale stated in a document, Water Security for Canadians, which was prepared in part to support the lobbying initiatives for the creation of the Canadian Water Agency. So the project objective, it's rather straightforward and simple, really. The diagram on the left conceptualizes the entire objective. We want to model the entire water cycle. So that involves climate modeling, land surface modeling, and subsurface groundwater surface water modeling. And the focus is actually on groundwater surface water, and to evaluate the potential influence of changing climate on that water resource. To translate the numeric outputs from that modeling initiative into some societal relevant metrics and metrics that are digestible outside of a numeric environment, and to make as much of the input data and output from the modeling initiative available under an open data license to the Canadian government. So what is the project scope and timeline? It's a 3-year project, started in April 2021, and it expires at the end of March 2024. So we're just coming up to being 2/3 of the way through the project. So we're well advanced in terms of data assembly. That's pretty much complete. There's still a bit of data prepping that's taking place. And we're spinning up the initial models to validate or verify the underlying data sets and just the computational regime before building a finer model. And we'll talk a bit more about that down the road. So how are we approaching this challenge of modeling the complete water cycle? And as alluded to already, it's taking place in three stages or three components, and actually implemented under three different software elements also. So we're taking global climate data sets and downscaling that to regional climate scales of 12.5 kilometers with using WRF, the Weather Research Forecast model. And that will be done for two components, the historic time frame and also forward model projections of mid-century and end of century. Now, to support the climate modeling and pairing it or integrating it with the groundwater surface water modeling, we're also doing a fairly extensive land surface modeling to constrain some of the thermodynamics of the near surface, evapotranspiration, soil temperature, soil moisture effects, and combined, those two modeling initiatives form the boundary condition to drive or force the groundwater surface water modeling, which is occurring in hydrogeosphere. And that discretization of that modeling initiative is occurring between 1 to 5 kilometer scale. And we'll get into a bit more detail on that later. So just to touch on the climate modeling then, that's largely driven out of the University of Toronto and the Canadian Forestry Service. So historic climate observations come from Environment Canada. The Canadian Forestry Service has a long history of trying to regionalize those point measurements that Environment Canada has, so providing a spatially continuous surface of precipitation and temperature data for Canada. The regional climate change modeling is taking place at the University of Toronto with a postdoc and Andre Erler, who's at Aquante. And both of those data sets come together in that the historic data set provides constraints on the regional climate model and understanding of bias in that modeling and some of the reanalysis products for the land surface analysis. And then that, as already noted, is fed into the hydrogeological simulation. And a lot of the modeling that's taking place for the land surface is at the University of Toronto with Chris Fletcher and graduate students. So for the regional climate prediction modeling, then we're taking the global modeling for North America and downscaling that. And one of the significant reasons for downscaling and working on the climate model data sets is global data sets don't include lakes. And the graph on the right quickly highlights the significance of large water bodies across the Canadian landscape, from Lake Ontario progressing all the way up to the northwest and north to Great Bear Lake in the northern part of Northwest Territories. Modeling lakes, as anyone in Southern Ontario appreciates, has a profound impact on the local climate, particularly downwind of those lakes, both from a precipitation and temperature perspective. And lake modeling is a bit of a challenge, and there are a number of lake models that are being employed at U of T to try and produce the best outputs possible. And this slide just highlights then for the historic period of 79 to 2018, the kind of impact that the lakes have on precipitation and around the Great Lakes, and also how different lake models are reflected in modeling of ice cover. And you can see that some lake models better reflect the ice cover relative to the observations in the top left of that diagram, with flake providing the best iteration in the winter time. And in summer, GL25 tends to provide better simulations. So that covers sort of the large scale, continental scale of the climate modeling. And for the numeric modeling in groundwater surface water, we're subdividing continental Canada and Baffin Island into 7 domains. They're all drainage based delineated. and include all of the transboundary watersheds with the United States along the southern margin in Alaska. And Baffin Island is separated out as its own independent domain just for simplicity and also based on uniqueness. So some of them are recognizable: the Mackenzie Valley watershed, the Nelson River watershed across the prairies, the Great Lakes St. Lawrence, which we then merged with Atlantic Canada. And the other three domains are delineated by drainage into respective oceans. And the MES resolution or discretization of the model is occurring in a finite element regime and will be completed at 2 resolutions. The coarse model incorporates 5th order Strawler streams and approximately a 1 kilometer discretization along rivers. And once we've verified all of the process and inputs and modeling regime, we'll develop a finer resolution 4th Strawler order stream model, which goes down to approximately 500 meters along 4th order streams. You can see the relative node counts per sheet and total. So from a time stepping perspective, there's a number of time steps taking place, and this diagram just works, shows HGS is the groundwater surface water model at the top, the climate modeling is at the bottom. Climate modeling is taking place at about a 3-hour interval with output. And likewise for the land surface modeling, that's aggregated to a daily time step, and then for input into HGS, a monthly time step. And the diagram, the right-hand side of the diagram can be divided into 2 components, the calibration period or the historic time period. HGS for the historic time period is being run on a daily basis. And then for the mid-century forecast and end-of-century forecast, HGS is being run with monthly outputs. And of note is that the climate modeling and land surface modeling is run continuously all the way through the 21st century. HGS is being run for discrete time intervals around mid-century and end-of-century. So to build a hydrogeological model, unlike surface water modeling, you do need a fair bit of subsurface data. And this diagram just highlights some of the key data sets in terms of hydrostratigraphy, soils, land cover, and permafrost, and then the temperature or environmental information. And that's being compiled seamlessly across all 7 domains, standardized where necessary, that various data sets are being integrated. For a number of surface and near surface data sets, the resolution is in the 30 to 250 meter range, so we'll support subsequent nested modeling. And then the data sets are all being parameterized for HGS. And, you know, unfortunately, modeling transboundary watersheds introduced a number of complexities in terms of data set harmonization required across the international border and bringing in American data sets. So there's certainly been no shortage of challenges, even with Canadian data sets. And it's not until you really start working with these data sets that you start to understand some of their limitations. And those limitations may be related to their extents, constrained by jurisdictional boundaries. It may be because the data is collected over a long period of time and requires normalization across data collection episodes or periods. It could be that it lacks the classification or attribution necessary for you to actually bring the data together or to extract components of the data that you need. And then, as most of these data sets are collected for other purposes, commonly they lack the parameterization that's necessary for running the Hydro-G model. So that's mostly behind us at this point. There's a few loose ends that are just being tied up. So hydrostratigraphically then, we've taken a highly conceptualized approach to the hydrostratigraphy of Canada. It's going to consist of 8 layers. And you see here they're numbered from 1 to 8, 8 being at the ground surface. And just working down from the top to the bottom, there's going to be, the soils will be separated into 2 categories, 0 to 0.5 meters and 0.5 to 1 meters. Then there's superficial geology of 2 to 3 layers, depending upon which basin we're in, and then 3 layers everywhere for bedrock. And some of these layers, for example, are constrained by map data, soil maps, superficial geology maps, and the bedrock geology maps, and then some information on subsequent underlying units, and trying to represent weathered or fractured elements at each of these interfaces. And just for reference, then, as we're talking about Ontario and Southern Ontario specifically, this just highlights two modeling initiatives that have been completed in either Southern Ontario or the Great Lakes, and highlights the differences between those modeling initiatives and Canada One Water. So the Southern Ontario model at 110,000 square kilometers with 17 hydrostratigraphic layers compared to, for just bedrock, compared to the 3 for Canada One Water, and another model for all of the Great Lakes by Zhu et al., highlighting a similar number of models. So providing us with some context in terms of building out from these relatively large regional models, but to even larger regional scales. And we have preliminary results from a number of drainage basins at this point for the coarse model. And the good news is that we're seeing good correlation between stream gauge information and model outputs at an annual and seasonal scale. And what we're really looking for in the climate model prediction stage of mid and end century is being able to model seasonality. So can we pick up both long-term climate change progression, but also changes in seasonality within that? And so we're hoping that these model results will be of use to a broad range of individuals and groups. And this slide just sort of highlights some of these communities. The communities may be societal, cultural, they may be economic, or governmental, in depending upon how you want to use that word, community. And so some of those communities will be interested in the actual technical outputs or data inputs that were used and can be used in other modeling environments, and some groups will be more interested in, say, metrics that may pertain to the impact of climate on groundwater, surface water. So we're hoping to provide accessibility both through a web-based portal at Equante, the Groundwater Information Network with the Geological Survey of Canada, and also produce hopefully some derivative dashboard or type metrics that are easily digestible. So we're about to release a progress report for December. Every 6 months we have a progress meeting. The 2022 December meeting is accompanied by this progress report, which will be coming out in early March for anyone who's interested, and its release will be broadcast via the project website, Canada One Water, and if you're interested in getting a copy. So in summary then, we've synthesized national scale data sets to facilitate this groundwater surface water analysis. We're updating regional climate model projections for North America based on CMIP 6. We will have a fully integrated, physically based national scale groundwater surface water modeling framework that will support mid and end of century projections and open access for data sets and outputs. And I'd just like to highlight a talk that's occurring on Thursday, 2 talks related to, or that are part of Canada One Water or relate to it. Tariq is presenting on monetization of ecosystem services, and Stephen Fry, if he's healthy, or Omar, will be presenting on nested modeling results from Southern Ontario and spatial scales. So thank you very much.